Welcome back. This is Larry Benko, W0QE, and this video is an introduction to transmission line transformers. And it is going to take more than a single video to do justice to this topic. Before trying to define what constitutes a transmission line transformer, let's look at the properties of a transmission line via SimSmith. I've created a circuit here with a generator, a ruse block, and a load. We're not using the load, which is why I've set it to 0 ohms. The ruse block contains a transmission line. There are 5 parameters for transmission lines if you don't give them a name for a specific transmission line type. But there's 5 parameters: length, impedance, velocity factor, loss, and and what frequency the loss is measured at, if we go through all 5 of those. But if I leave parameters off, I get defaults. In this case, I'm going to define a length and a transmission line impedance only. That's a differential or surge impedance right here, and it's a lossless transmission line. I monitor what's going on by 4 resistors that are 1 micro ohm each, so that I can look at the currents in all 4 of the leads in the transmission line. I have a 50 ohm load, which matches the 50 ohm impedance of the transmission line, and I can either ground the center of it or ground the top of it or ground the bottom of it, and I can measure the currents everywhere I want. So let's look at what we get when we start off with this circuit like this. If I click on, and I've done some written some scripts here so I can look at the currents in these components. So let's look at R1I. That's the current in resistor 1. Now, with a 1 watt signal coming in here, 50 ohm impedance, that is, we will see 7 volts on the output and 141 milliamps. 141 milliamps is 200 milliamps peak. There's 200 milliamps peak. 200 milliamps going into R1. R3. Notice the phase. Notice the dots on all these components. They're all the same direction. We should see R3 be the same as R1, but delayed slightly. Let's look at R3. It's delayed slightly. If we increase the length of our transmission line, the delay gets longer. And we're measuring this at 10 megahertz. And if we look at the current coming out of the transmission line on the generator side, we would expect it to be equal and out of phase to the current that goes in. It is. It's equal and out of phase. That's a requirement in transmission lines if you want them not to radiate. At every point along the transmission line, the currents in the 2 conductors must be equal and out of phase. So if we look at all 4 currents now, what we see is the blue being the input current, red being the output current on the top side conductor of the transmission line, and on the bottom side, the same thing happens. Now let's look at the current into the load. Well, not the current, let's look at the power into the load. Since we do not have a connection to P1 here, we have to write our own formula for power. Well, that's pretty easy to do. We say power. I have stroke 5 here, means I want a bold line of 5 dots wide. And I want the power in resistor R5 plus the power in resistor R6. And that will be the power in my load. So I click on that. I'll move that down a little bit. I see 1 watt. 1 watt generator, matched load, lossless transmission line. We expect 1 watt in the output. 1 watt's what we get. We look at the SWR. We see this new feature, which is an arrow, which is reminding me that I've got something that's either out of bounds on the bottom side. It's blue, so it's something that's selected that's blue. I have to, and it turns out it's SWR. If I move SWR up just a little bit, you can see that the arrow goes away. The arrow is kind of annoying, but it's also kind of a nice feature in that it reminds you that something's out of bounds. SimSmith does not do any kind of auto adjustment on the axes. So if you plot something that's out of bounds, then it just is out of bounds, and it's up to you to go find it. So this is exactly how you expect the transmission line to work. This is what's called in some textbooks the odd mode of transmission lines, odd or differential. And when you see that in a textbook, they also mention an even mode or a common mode way for transmission lines to work. And let's look at that now. So what we'll do is we'll drive both sides of the transmission line from the same point with respect to ground. We have the output connected to ground. Now, there's 25 ohm resistors in there, so we'd expect to see a 25 ohm impedance on either side if there was no common mode impedance here. If there's common mode impedance, we'd expect to see something less. Let's look at what we see. And we see R1, R2, R3, R4, all low. Let's look. Way under a microamp. So if they're way under a microamp, let's just say it doesn't matter. There is some residual small currents that flow here, and that has to do with some impedances SimSmith puts in that are kind of out of sight to the user, and they deal with making the circuit not blow up mathematically. And there are a lot of times there's 1 gigohm resistors placed in various places, but we're talking about thousands of times less current than what's flowing normally. So let's just call that current 0 effectively. And what we're going to do here now is take the length of the transmission line and drop it down. What if this transmission line, well, if we drop it down that low, we start to see some little current, but that's a femtofoot. Let's drop it down to, say, 0.001 feet. That's 1 millifoot. 1 millifoot is effectively 0. If we were to do something like this, most people would say, with a piece of transmission line this small, this point in the generator is basically connected to ground, and we have shorted out the generator. Yet, SimSmith does not predict any current flow to speak of. And that's because SimSmith assumes that the common mode impedance of this piece of transmission line, which is different than the differential mode impedance, the common mode impedance is pretty much infinite. If we want to define a common mode impedance, it is up to us to define it. We can define it by putting something like a resistor. If the impedance is going to be resistive, actually it could be inductive too. We could put something in here that would be a complex number. But if we made a number here that we put something in here like 1,000 ohms, and we did that on both sides, we now will see current flow. Current way more than we saw before. And that's with 1,000 ohms here. We see 17 milliamps or whatever. So it is up to the user to put the impedance across the transmission line that represents the common mode impedance, if that's part of the circuit and if that's important. And it turns out it is important in transmission line transformers. But we're going to leave it out because it also makes the circuit more complicated and a little harder to understand. So we won't worry about it when we figure out how things work, and we'll worry about it whenever we want to actually build something, if that makes sense. The next thing let's do is bring a different circuit in. And this circuit is 2 transmission lines. And I just wanted to do this for a moment to show again the common mode impedances and how they start to play in a transmission line transformer. Here what I have is 2 transmission lines driven in parallel from a 50 ohm source, and each one of these is terminated in its own impedance. So we have Z01, and we make, so this is a 50 ohm piece of transmission line, this is a 50 ohm load, this is a 50 ohm transmission line, this is a 50 ohm load. We'd expect to see 25 ohms back here. So let's see if that's correct. And we go back to the Smith chart, and what we see is 25 ohms. We're sweeping it. It's 25 ohms without regard to frequency. And I mean, looking at it from this view, it's without regard to frequency. Obviously, there's little component things that will get in the way later, but this is very interesting because now let's change this circuit to be this. Now what we did is we stacked up these 2 on top of each other. We stacked up the resistances. We stacked up the voltages on the output of the transformers, or on the output of the transmission lines, and both of them are in phase, and we still have 25 ohms. We can also tie this point together if we wanted to. Whoops. we will still have 25 ohms. The power of being able to have these with some voltage reference to ground and have the outputs have a completely different voltage reference to ground is a very interesting property in transmission lines, and something that we take advantage of in transmission line transformers all the time. And real quickly, if we look at two transmission lines in parallel, driven in parallel and the output in parallel, they act as a single transmission line of a different impedance provided they have the same electrical length. And let's look at that for a moment. There's two transmission lines, are both 50 ohms apiece, they're both 3 feet long, and I see plot on the Smith chart looking like this. The load impedance is incorrect to give me no rotation. 25 ohm load impedance. These two transmission lines, a 50 ohm and 50 ohm in parallel, give me a 25 ohm result, swept over frequency. So this acts as a 25 ohm piece of transmission line. What happens if one of these is a little bit longer than the other one? Well, if we start changing the length here, not a whole lot. There's a half a foot difference. Swept up to 100 megahertz, our impedance only varies from 25 plus J0 to basically 24 minus J 3.35. It's not that critical in many cases to get these exactly the same length. And SimSmith shows us that very nicely. We can also take these two transmission lines whoops. And drive them in series. These two transmission lines driven this way look to be 100 ohms. And let's see if we can show that. If I increase my load impedance to 100 ohms, we see that we have a resistive match again over frequency to 100 ohms. Now, does it matter if these 2 points are tied to something? It does, as long as if this point is tied to ground. So generally these are left alone, and these wires just connect each piece of transmission line. But this is a way to increase the impedance. What if they weren't the same impedance? What if this was a 50 ohm and this was a 75 ohm piece of transmission line? Does that work still? What output impedance do I need to have to get it to match? 125 ohms. It's the sum of those two. And we could have done the same thing with them in parallel. You can have parallel a 50 ohm and a 75 ohm transmission line in parallel. Look like they're, I'm going to use the same formula as you use for resistors. So it's 50, 1 over, plus 75, 1 over equals 1 over. It's a 30 ohm transmission line. So you can get different impedance transmission lines than you think you could by having transmission lines in parallel. Again, if this length of this one changes by a foot, we don't see a lot of action. This is just another interesting thing to keep in mind. Now let's look at the simplest transmission line matching problem we can do, and that is a single transmission line of some impedance and some length. And let's again make this a lossless piece of transmission line, velocity factor 1. None of this really matters again, and it has some length. We'll start off with 100 feet. And it has an impedance 50 ohms. I want to match some starting impedance. And it really doesn't matter where my starting impedance is, but I'll pick some point here. We have to make this a little bit shorter, a little bit smaller. So here's our starting point. We can drag our starting point in SimSmith anywhere we want. Let's drag it up to let's drag it to there. Can I match from this point to 50 ohms with a single piece of transmission line? And the answer to that is yes, I can. So I change the impedance of the transmission line, and then I change the length. And there I've done it. What about if the impedance is, say, there? Can I match? And the answer again is yes, I can. I can match everywhere within this circle and everywhere within this circle, but I cannot match any point with a single transmission line that's out of there, out of those two circles. So this area up here I cannot match. And it doesn't, and so what you usually do when you want to see if it matches is you make the length long, you sweep the impedance of the transmission line, and you see if somewhere you can get the arc to go through the point you want. Well, the point I want is right here, and there's no way in the world no way in the world I can get this to go through there. If I move this point close to the edge, I can see that if I make the transmission line impedance very high, and then of course an appropriate length, oops, going the wrong way. I can get close. So a single piece of transmission line can be made to match one half of the Smith chart. It can match the area in this circle and the area in this circle. However, you're totally at the mercy of what the impedance of the match is, and you may not like the number for the impedance of the transmission line. Maybe something you can't get a hold of. So that circuit typically isn't used. Although, if you have something that's close and gets you a pretty good match, a lot of times a single piece of transmission line is the best choice. Now, if we want to go to something a little more complicated, we can do two pieces of transmission line. So let's take this same point right here, and we will say we have a 50 ohm piece of transmission line, and let's also have a some other impedance over here. If I put this side being a 50 ohm transmission line, it doesn't do it doesn't do anything. But if I make it 75, say, and make this long, and again, let's go back to zero loss. Now, is there some length here that we can use? We're getting pretty close. And we change the length here. And that's pretty close to a match. So with two pieces of transmission line, we can often get a match with transmission lines that are readily available. Other ways we can do it is we can do a transmission line with stubs. We can do sectionalized transmission lines. All of these, though, if we look at the SWR plot, what we see is a relatively narrow band match. And all of these single transmission lines, multiple transmission line circuits give us a narrow band match. A lot of times we want a really wide band match, and that's a topic for the next video. But right now, let's continue on with one more example. Now here's another circuit where we have a 90-degree or quarter wavelength piece of transmission line, and we're going to match from 6 ohms to 50 ohms. It's over an 8 to 1 impedance range in matching. And we do that with a transmission line whose impedance is the geometric mean of the desired match range. So we take 50 times 6, which is 300. We take a square root of 300 and we get 17.32. If we put a 17.32 ohm piece of transmission line in here that's 90 degrees long, we see that we get a good match at the desired frequency, and the match range is fairly narrow. It's less than a megahertz wide, as is indicated. Let's set this through 1.5 to 1 for the match range. And we see up here match range is between, say, 9 and 11 megahertz. And just remember that, 9 to 11 megahertz. So it's about a 2 megahertz range. We can also do this by using two pieces of transmission line, where the first piece gets us part of the way to our match goal, and the second piece does the other piece of the match. And here's an example of that. And there's some formulas that tell you where to put these impedances, but they're basically you set the mean here to be the geometric mean of these two, and then you match to that point, and then from that mean to the final goal. But what we see here, let's make sure we're doing it the same way again. Okay, 1.5 to 1, and now we see that our range goes, instead of from 9 to 11 megahertz, it goes from 7 to almost 13 megahertz, which is a big improvement. And we can play some games. We can make this range a little bit wider if we let this SWR in the middle come up a little bit more. Let's maybe something like that, and then that gets us even a little bit more range. But we can see that we by using two sections, we can increase the bandwidth. And then finally, I have one more example here where I've used 4 sections, and we can see that the bandwidth is even increased more. The bandwidth goes from 4 to 15.7 megahertz. And we can see that this actually matches more than half the spectrum. But if this is the match range, and then this is the match range, and then this is the match range, we could build 2 of these networks, the second one being staggered with the first one. We'd have, and if you could switch between them, you could match from 6 to 50 ohms over a wide range of frequencies. But you would had to have come up with these 4 individual sections of transmission line. Now with four sections, you are capable of doing some things. You don't have to have the right answers for all these match points. You can match to a different intermediate point that's close and be good. We could set this, say, this is only 6 ohms instead of 8 ohms, and another one is a different impedance. We can change the links somewhat and play around. It's pretty interesting, but you can get a pretty good match range with a little bit more flexibility in impedance ranges for the transmission lines than you might have otherwise thought. But again, this is considered to be somewhat of a non-broadbanded match. The next video will be about specific, very broadbanded matches, and that's what people mostly think of when they talk about transmission line transformers. But all these examples I've done so far have really been transmission line transformers also. They've achieved the transformation in impedance without any flux coupling via core or anything like that. They do it just within the transmission line mechanism itself. Hope you've enjoyed this video. The other video should be out just in a couple days. And let me know if you like it. If there's pieces I missed, if there's something you'd like to see in more detail, let me know. Thank you very much.